I'd like to welcome tonight Professor Sergei Guriev from the Institute of Radio Astronomy and Space Research. He's obviously, if you've been in society for a while, you would have seen a number of his talks over the years. They're always really top value and often entertaining as well. And it looks like a really interesting topic tonight, how radio telescopes can be used to get better angular resolution in the Gaia space satellite for position on the sky and some other topics. So thanks very much for coming along, Sergei.
Thank you very much for inviting me. And hello, everyone. Hello, our people who watch us on the web. I hope there are a few. We will see if they ask questions later. So today we will talk about geometry. Astrometry. Astrometry is geometry of cosmos. We measure positions of objects, their velocities. So basically we talk about 6 dimensions, 3 dimensions in terms of position in space, and 3 dimensions in terms of velocities. We know not only where it is, 3D picture of the universe, but also where these objects move and what kind of streams they create and all this kind of very interesting things. That's about modern astrometry. And this picture is, of course, our Radio Astronomical Observatory at Warkworth. And I always point at this car, that's old car of Tim Natush, who is the deputy director of our institute. And also, I think Tim has the title of the friend of the telescope, which is very high in radio astronomy. Yes, 12-meter radio telescope, 30-meter radio telescope, and today, after quite a big introduction, I will talk about some projects that are conducted in our observatory with the help of these radio telescopes. So, yeah, the distance, cosmic distance ladder, you probably heard this term, how we determine distance in space. And there are different methods that we use in order to find distances and 3D position of objects in the universe. And on top is the redshift, which allows us to determine distances of the most remote objects like active galactic nuclei, quasars, galaxies, and so on. And here in the bottom of this is parallax. I like this distance scale ladder more that shows this parallax in the bottom, in the foundation of everything. That's direct geometric measurement of the distance of objects. And all other methods are based on this method. And today we will talk about this very long baseline interferometry, MESA, VLBI, and other things connected with radio astronomy. So, parallax. I created this quite recently using some pictures from the internet, like looking at this object and very remote objects. And we close one eye and we see this object among these stars, and then we close another eye and we see this object among these stars. And instead of this terrible person, we can use the Earth with some baseline and measure this arc between 2 positions of this object among remote stars. We measure this arc on the sky between stars. And this angle obviously is equal to this angle. This is what we call parallax angle. and we have the baseline, and we can write some trigonometry, which includes baseline and this angle and distance of this object. Instead of the Earth here, we can use, of course, much greater distance, the orbit of the Earth around the Sun, and we look from different directions at a star, and we see that during 1 year, this star, if it is located like perpendicular to the plane of our the Earth's orbit, perpendicular to the ecliptic plane, we see this circle among the stars. Wow, fantastic! And we can measure this arc, and which is like twice this angle, and this angle is this angle, parallax angle, and we have a formula, and I used Excel to do some calculations. The formula becomes very simple when the object is far away, when angle is very small, this tangent or sine function becomes just, we can substitute with with the value of this parallax angle. So P is parallax angle. It is equal to 1 over d. D is distance of the object, or vice versa. Distance of the object is 1 divided by parallax angle. And this is if we use parallax angle in arc seconds and d in parsecs. Fantastic, very simple formula. And in this case, if parallax angle is 1 second of arc, then the distance is 1 parsec. If parallax angle is 1 millisecond of arc, 1/1000th of second of arc, the distance of the object is 1 kiloparsec. If it is 1 microsecond of arc, microarc second, the distance is 1 million parsecs, 1,000 kiloparsec. It's not that simple, actually. If we measure angle with 10% accuracy, then 0.1 allows us to the accuracy of parallax measurement of 0.1 arc second allows us to measure distances of 1 parsec with 10% accuracy. If it is 1 milliarc second, we can, so it is all a little bit less optimistic than we would think. Accuracy of parallax required to measure distance with 10% accuracy, 10% error is this. You need 1 milliarc second accuracy to measure distances of objects at 100 parsecs with 10% accuracy. That's typical picture in the internet. I just thought, oh, I will just take any picture of, I type parallax and image, and then 1,000 images. They're all like this. They're all wrong. Oh my God. Okay, let me explain. So let me just turn it. And this object, according to this picture, creates this oval here. But these stars are not far from this object. So we expect them also create this. So how to measure the distance of this object? They all would shift. It is very important that these background stars are much, much farther away than this object. This is a little bit better. I did it. I designed this myself. So I was desperate. I couldn't find the right picture in the internet. This is a little bit better. And here is the orbit of the Earth and the Sun, and it's in the center, and the star, and we measure this arc between two projections of the star at different period of time. For example, today in June, it is projected here, and in 6 months' time, in January, it will be projected here. Wow, fantastic. and we have this angle. This angle is equal to this arc, and this angle is equal to this angle. But wait a moment. This angle is equal to this arc if we look from the star, but we are not on the star. We are parsecs away from the star. We look from, well, maybe from here, from the Earth in the middle position. I put it from the sun, but doesn't matter. Yeah, and this angle is not this angle. It is not, and this arc and this angle are not connected with measurements conducted from this star. So there is a difficulty here, and it's something we need to think about when we discuss parallax. And from my teaching practice, I know that this is one of the most difficult questions to ask students. They think, oh, so simple, so straightforward. And then when they start answering assignment or test, I see no understanding. So anyway, okay, let's go to bigger baselines. Here the baseline was our orbit of the Earth around the Sun. Diameter is 2 astronomical units. Radius 1 astronomical unit, but this recently was done very good with New Horizons. So here's the Earth with its orbit. That's what I just showed. This orbit is here, tiny one. They even didn't, well, sorry, it is in German, yeah, Erde, yeah, die Erde. And they even didn't show Mars here. So it is tiny, and parallax of this object would be this tiny one. You can hardly see this displacement, but New Horizons now is at 50 astronomical units. And instead of 1 astronomical unit, we have, or 2, we have baseline of 50, 25 times greater, and this shift is much bigger. And oh, it works. We're never sure if our animation would work. It works. So this is Proxima Centauri, the star with stellar magnitude 11.1, apparent magnitude as visible from Earth and from New Horizons, 50 astronomical units baseline. And parallax, by the way, measured by Gaia, not from this observation, is measured in milliarc seconds, 765.066 plus minus 0.050 milliarc seconds. Wow. Well, I remember that it is 0.77 arc seconds, but here we definitely need to use milliarc seconds, and the accuracy is phenomenal. This is Gaia. And EDR means Early Data Release 3, which was published just a year ago. And another star, this is Wolf 359, magnitude 13.5 in constellation of Leo, also from Earth and New Horizons. And this is displacement because of parallactic shift. That's what we just talked. Projection of the star on very remote background of stars is changing as you look from one place and another place in space. And this parallax is also measured by Gaia. And accuracy, you can see like 60 milliarc seconds, 50, 0.05 milliarc second, it means 50 microarc seconds. And about 70 microarc second. What is this angle, milliarc second, microarc second? Let me show you something. 20 cents. It is 10 milliarc seconds if this coin is placed on the surface of the moon. 10 milliarc seconds. Here we talk about microarc seconds. Can you imagine what kind of angles we actually see? This is human hair. I will not show you, I don't have enough. Okay. Gaia is a champion. Is it a champion? Okay, we will talk about it. I will tell you later that actually VLBI is a champion in measurements of parallax. And this is Gaia Early Data Release 3, and it is December 2020, 1.5 years ago. And they write this, and I just don't try to read it. I put it here on this slide. So Gaia Early Data Release 3 published 6 coordinates of 3 coordinates in space and 3 coordinates in terms of velocities. Velocities in X, Y, and Z direction of 1.5 billion stars. And the median uncertainty in parallax and annual proper motion is 0.02, 0.03 milliarc seconds, which is 20-30 microarc seconds. Remember this, 20-30 microarc seconds. When we will talk about VLBI, we will talk about several times higher accuracy, 10 microarc seconds. And I will explain this. G is the the band that they use. Basically, it covers all optical band. And it is 500 microarc seconds, or 0.5 milliarc seconds, 500 microarc seconds at magnitude 20. Hipparchus was much worse, 0.61 milliarc seconds, so it is like 30 times Gaia more accurate than Hipparchus, the first astrometric satellite. Yes, and let me tell about a few achievements which were immediately published soon. It was December 2020, and this paper is February 2021, the Astrophysical Journal Letters. And what they did, let me show you again here. In combination of best complementary sources of Cepheid calibration, we reach low precision, find Hubble's constant, 73.2 plus minus 1.3 kilometer per second per megaparsec. And it is 4 sigma difference with prediction of Planck cosmic microwave background observations under lambda cold dark matter model in the universe. And they say, we expect to reach 1.3 precision of near term from expanded sample of 40 supernova 1A in Cepheid hosts. Let me explain what it means. It's not easy to digest immediately. That was published 1 year after, in January 2022, this paper. And they looked at 41 galaxies with high redshift. They are pictures of Hubble Space Telescope of these galaxies. And look, in all these galaxies, there took place very important events, supernova 1A explosions. And supernova 1A is a standard candle to measure expansion of the universe, to measure Hubble constant, to measure amount of dark energy, how it is expanding with acceleration or not, or all this. That's the main tool for us. So these galaxies, and look at some of these galaxies here. You know what are these red points? They're Cepheids. They're variable stars, supergiants, very bright. And Gaia did photometry of the Cepheids and determined distances of these objects where supernova explosions took place. So Gaia, through this distance ladder using this observation of Cepheids, reached the highest level of the distance scale ladder and determined rate of expansion of the universe. And what they published in 2010, the inclusion of high redshift supernova 1A yields Hubble constant 73.30 plus minus 104 kilometer per second per megaparsec. We find 5 sigma difference with the prediction of Hubble constant from Planck cosmic microwave background observation under lambda cold dark matter model, with no indication that the discrepancy arises from measurement uncertainties. The source of this now long-standing discrepancy between direct and cosmological routes to determining the Hubble constant remains unknown. Oh, I love it when they say remains unknown. It means that next generations of astronomers will have something to do, a lot to do. Before I go to the next slide, where I will talk about this discrepancy more in detail, let me explain what does it mean, Hubble's constant 73.3 kilometers, let's say 70 kilometers per second per megaparsec. So if the object from me is 1 megaparsec away, it means that in average, due to expansion of the universe, it has velocity 73 kilometers per second. If it is 2 megaparsecs from me, it means that this object's 73 times 2, 146. If it is 3 megaparsecs away, it is 3 times, it's 73. 73 shows what happens each megaparsec away, farther and farther away from me. Expansion of the universe. Right, and this, let me turn it. So that's values of Hubble constant, expansion of the universe. Here is measurements based on Cepheids and Gaia, this band, and it is very small error, just plus minus 1. And here this pink band shows measurements made with Planck mission, cosmic microwave background radiation, in the framework of lambda CDM model. When there was the first data release of Planck observations, I was there in this conference. It was in California, in Pasadena. And they were very nervous. They presented all this data, and a lady, French lady, presented this data, these results. And I asked her, did you consider another model, like not necessarily cold dark matter, maybe warm dark matter or hot dark matter? It means a dark matter which interacts with normal matter. Cold dark matter means no interaction at all, and we don't know what is dark matter, by the way. And she said, no, we were in such a hurry to present this that we didn't consider any other model. I'm not sure if now they're considering, because this discrepancy is absolutely obvious. It should be explained, and they have no explanation if they use this model of Planck, because this is based on geometry, on very, very, very good knowledge of parallax and Cepheid parallax. Right. The Gaia Sausage is another achievement of this third early data release 3. What does it mean? Okay. Sausage, that's what they call sausage. This is a graph, actually. And sometimes astronomers are, they need some humor in their night work. So they called this sausage. So in the galactic disk objects, if we plot this axis, they would form this spot, this sphere. And the sphere says these objects have circular velocity about 200 kilometers per second, moving around the center of the Milky Way galaxy. That's their orbital velocity. And radial motion, it means that from the center I would start going towards Steve. That's my radial, or closer to the center. They're all here. They don't have this radial motion. They just have orbital motion around the center. And Gaia found the whole population which has no circular motion, but quite significant radial motion away from galactic center and towards galactic center. So that's Gaia Sausage. This shows this population, galactic plane of the galaxy, and stars going in different directions towards and outside. Actually, that's very interesting picture. It shows something very important. Gaia is very good in measuring distances, velocities of objects which are not in plane of the galaxy, not in galactic plane. In the galactic plane, everything is difficult because there is gas and dust, and optical telescope cannot see through gas and dust. Above, fantastic. Below, great. And you can see that Gaia discovered this. And if we look from different perspectives, they are streams of stars going towards galactic and away galactic plane, and they actually tell us about mergers with other galaxies, maybe small dwarf galaxies, and these mergers create these streams of stars. That's a discovery of Gaia. And I just mentioned that in terms of this is center of galaxy, and this is part of the galaxy where we are, and here is the sun. And red dots show where Gaia measured positions and velocities of stars in the plane of the galaxy. OB stars, they tell us about areas of star formation which happens only in the plane of the galaxy where we have gas and dust. And you see, this is it. That's what Gaia is capable in the plane of the galaxy. But, oops, what happened? Maybe I need intervention. It's okay, I'll do it. Yep. Yeah, you see this discovery of Gaia Sausage. it is not in the galactic plane. But we know that we have spiral arms. Where are the spiral arms? And look at these points here beyond Gaia. What are they? They are actually radio astronomy data. And let us go to early 70s, no, mid 70s, 76. Spiral structure of our galaxy determined from H2 regions. H2 regions are areas of star formation. There was cold molecular cloud, then a star appeared due to collapse, and the star, with its ultraviolet radiation, ionized gas around, and we see this area, bright area of ionized gas, like the Orion Nebula, Omega Nebula, and so on. So that was the map. And spiral arms were traced quite nicely in the middle of 70s, radio astronomy, radio astronomical observations. And I'll show you something, 2017, Alberto Sana, Mike Reed, and a few more authors. They used very VLBA, Very Long Baseline Array, in the United States, and they also traced these positions of Milky Way galaxy spiral arms with the help of molecular masers. In particular, it was done with help of water masers, H2O. And do you see something special in this picture? Something outstanding? Something that makes you like, wow? No? Okay, this is this point. They measured the distance of this object, so the sun is here, the center of the galaxy is here, and this is from the center another 12 kiloparsecs. Measured with error, with accuracy plus minus 10% or maybe 15%. But it places this object quite confidently in this outer Scutum Centaurus arm. That's the one. 2017. And that's the measurement of this parallax of this object, and parallax is measured. It is in milliarc seconds, and you can see that the uncertainty is 0.006 milliarc seconds, which is 6 microarc seconds. This is H2O water maser, 22 gigahertz frequency that allows to reach this incredible accuracy with the help of VLBI, Very Long Baseline Interferometry technique. So what is this technique?
Well, so can I just ask, that object, is that right on the plane of the galaxy?
Yes.
Okay. So
right through gas and dust.
okay.
Transparent for radio waves. So what is Very Long Baseline Interferometry parallax measurements? We have radio telescopes, different types of radio telescopes. Can be single dish with quite big beam. They can be array of telescopes, phased array of telescopes. That can be a radio telescope with focal plane array, which has several beams. Why we need several beams? Because when we look at our target object, we need some objects for comparison. We also need to look at some other objects. And in radio astronomy, remember, I started from this wrong picture. The object that we are interested in, the star we want to determine distance, and background stars, they are how far they are. The farther the better, but they are stars of our galaxy. In radio astronomy, our reference objects are quasars. They're the most distant objects in the universe, and so that's our great advantage. Then you can see that this is the formula. What we measure delay in arrival of the front of electromagnetic wave that comes from this object, the parallel wave on this distance. And this delay, tau, is time of delay multiplied by speed of light, is dot product, okay, is product of the baseline vector and vector that shows us direction, exact direction to the object. And if we know this baseline with high accuracy, and this is one of sources of error, and we try to determine the center of the radio telescope with sub-centimeter accuracy, better if it is millimeter accuracy, that's a lot of work should be done to reach this accuracy. In this case, we can determine position of this object on the sky with very high accuracy and reach this 10 micro-arcseconds. The problems also are ionosphere, troposphere. I need to look at time from time to time. Where are we? Oh my God. I don't have much time. Bill, 10 minutes?
No, sure, just...
Okay. Okay, so ionosphere, troposphere are the problems. They are different in different locations, in different continents, and very long baseline interferometry, we use like thousands of kilometers between radio telescopes. This picture shows just objects for comparison, and reference objects are quasars. They do not show parallactic shift, which is huge advantage. That was preliminary experiment in 2017 using radio telescopes in Australia, in Hobart, in Ceduna, in Yarragaddy and Catherine. And here are objects, major sources in the galaxy, which are objects of our interest, surrounded with these reference sources, quasars. And next step, and this paper is in preparation, includes New Zealand Warkworth. And here two objects are chosen. And this is series of observations. And this object was observed before from the northern hemisphere, but this object is a southern hemisphere object, only visible from southern hemisphere with declination minus 56 degrees. So it was like practically pioneering work. I don't show you these results because it is not published yet, but I can tell you that accuracy reached is around 10 microseconds, which is 2-3 times better than Gaia accuracy. And also advantage that we can see through the galactic disk. Let's look at this. So this is accuracy reached, which is 0.01 milliarcseconds or 10 microseconds. And you can say, oh, you can see only to 10 kilometers if you, and your accuracy would be plus minus 10% in this case. Okay, we can see to 20 kiloparsecs, 20 kiloparsecs. Unfortunately, in this case, with our positioning accuracy. In this case, we would determine distance with 20% uncertainty. You see? Yeah. But, well, that's what we have. And the next step is improvement of this accuracy, and with a square kilometer array, for example, this accuracy will drop to 1 to 3 microseconds. So Maser VLBI astrometry allows direct measurement of distance promotion of individual young and evolved stars, calibrating their astrophysical properties, establishing accurate configuration of spiral arms. How many spiral arms do we have in Milky Way galaxy? 4. Okay. Refining parameters of galactic rotation and the local standard of the rest. And so refining distance to the galactic center. And let me show you advantage of the southern sky, where our observatory we are and where square kilometer array is built. So here, here are the objects, some measurements of the object with spiral arms. They presented in different color here, and the same objects on the plane of the galaxy. And this shows where objects which are accessible from the southern hemisphere. And if here we deal with 100 objects, here we predict existence of approximately 1,000 objects. We can do this mapping very, very well. Yeah. Right. A couple more works done in Warkworth, unprecedented change in position of 4 radio sources, and it is about reference sources. They are reference sources not only for our Maser VLBI astrometry, but they are reference sources also for International Celestial Reference Frame. International Celestial Reference Frame is the basis of all space flights. We need to orientation in the space, and this 4,500 quasars, active galactic nuclei, provide this reference frame where we can fly to different planets, to the moon, and so on. And this is done with the help of radio astronomy. Gaia found offsets between optical counterparts and radio source positions for several defining objects, so we decided to reobserve them with high positional accuracy using very long baseline interferometry, involving radio telescope in Australia, New Zealand, China, Europe, and position of 4 defining radio sources were found to have unprecedented shift. Here listed these objects, and the shift is shown. In 90s, their position was determined, and then people found that something's happening with this object, but they didn't pay much attention, and no one observed this object, 3C48. And these are our observations from 2017 to 2020. And even here we see some trend of changing position. And some other object, STA21, it was here and no one observed since then. Well, in 2015 there was one observation, but no one paid attention that there was shift. And these are our observation done in Warkworth. Another object, also old observations and new. So altogether 4 objects. Yeah, that's our observations. That's our observations. Why this happens? Because these objects have jets, and parts of these jets sometimes are very bright. So when you look in optics, for example, you just integrate, you don't see details. Only VLBI can show you details of this object and jet. And this is 96. And this is structure in 2017. This part became extremely bright, so it looked like this object shifted there, center of mass, so to say. This object also, you see, there was structure, and then this part became brighter than others, and now we think that, oh, where is this object? It was here, now it is mostly here, and so on. And finally, one more work, VLBI Astrometry of white dwarf pulsar. This is amazing. This is the only such object. Pulsars are rotating neutron stars with huge magnetic field and with flux of relativistic electrons moving almost with speed of light. And here, in the case of this object, it was discovered in 2016, radio pulsing white dwarf binary star. Let me explain about this binary star. It has two components, one M star, which fills its Roche sphere, lobe, yes, and a white dwarf. And white dwarf goes around this, they move around each other with a period of 4 hours. But this object shows pulses, which come with a period of 2 minutes. And these pulses come in, right, let me see, this is optics, this is ultraviolet, this is infrared, and this is radio, 9 gigahertz. I will show radio observations later. Yes, here radio observations 5 gigahertz and 9 gigahertz. And here is what we call Fourier Transform, and it shows 8.5 millihertz. Hertz is 1 divided by second. If you take this 8.5 millihertz, flip it around, you will have period, and period is about 120 seconds, which is 2 minutes period. And this is harmonic, 2 times greater frequency. This is a list of telescopes involved. This is Very Long Baseline Interferometry and Parallax, which we hope will allow to distance, allow to judge better about physical parameters of this unique object. This object has spectrum of synchrotron radiation, which tells that it produces relativistic electrons. This is very unusual. There should be huge magnetic field. So what is the nature of this object? There are several models, but they have problems, these models. I will skip this. Future of maser astrometry, SKA plus VLBI, or next generation VLA, very large array, plus VLBI. And for example, SK1 with mid-frequency receivers will cover hydroxyl spectral lines, methanol maser transitions. We work in this frequency in Warkworth, and we will be able probably to contribute to SKA plus VLBI because we have very good baseline with South Africa, more than 10,000 kilometers. Formaldehyde molecule, and accuracy is expected 1 to 3 microseconds. Now we reach 9 to 11 microseconds. SK2 and new generation VLA will allow to observe water masers at 22 gigahertz, and it means that accuracy will be even higher. I just placed here, I'm not sure if we have 2 minutes video about next generation VLA. Yeah.
The idea for next generation VLA was inspired by the VLA itself.
2 minutes.
The Atacama Large Millimeter Array in northern Chile. The NRAO, in conjunction with our science community, envisioned the NGVLA as a new large radio interferometer that will open up new discovery space in astronomy. Our idea for this is an instrument that is 10 times the sensitivity and 10 times the spatial resolution of the VLA or ALMA.
I am very excited about the data that will come from a next generation VLA. It will be exquisite in detail, the sensitivity will be unparalleled, and the opportunities that it will open up in many different science areas is really one of the things that excites me most, that this is a very open facility that anyone who has a great science idea can propose for and use, and its flexibility and its versatility enable many more science questions to be addressed than what we can think of right now.
The next generation VLA has been designed to accomplish 5 main science goals: unveiling solar system analogs, probing the initial conditions for life through astrochemistry, charting the assembly, structure, and evolution of galaxies over cosmic time, perform fundamental tests of gravity, and understand the evolution of black holes.
One of the things I work on is measuring the distance to stars in star-forming regions, and measuring their distance and how they move within the star-forming regions. Currently, we can only do 20, maybe up to 100 stars in these star-forming regions. The star-forming regions contain thousands, tens of thousands, hundreds of thousands of stars. With the next generation VLA, we'll be able to study 10,000 stars in these star-forming regions, which will help us give definitive answers to major questions in star formation.
The NGVLA will be a superb black hole hunting machine, the ultimate black hole hunting machine. The NGVLA's high-resolution imaging, combined with its fast mapping capabilities, will enable it to search for radio transients associated with gravitational wave sources, neutrino transients, and optical observatory transients, and identify those with black holes that are involved in violent merger events.
This will be fantastic instrument.
The idea for the
No.
inspired by the VLA itself.
Yeah. And before I click one more time to say thank you, I want to say that AUT continues collaboration with the Square Kilometer Array, and now we start collaboration with NGVLA, which physically will be in Americas, mainly in the United States. It will be a gap between SKA, relatively low frequency, where there are very important tasks for low frequency, and ALMA with very high frequency. There is a gap, and it will fill this gap. So, incredible future. Thank you.
Questions for Sergey? Yeah.
I have one question. Can you go back to your figure 3?
Sorry?
Can you go back to your figure 3? Back a few slides.
Figure 3.
Yeah.
You mean slide number 3?
No, not slide number 3. It was labeled figure 3. It was the one with the sine curves.
Okay.
That one.
Yeah,
Is there any reason for the, I don't know if this is a question that's an easy answer, but is there a reason why the error bars on the right ascension are so much smaller than the declination ones?
Oh, that's probably about orientation of the object with respect to the plane of ecliptic. Yeah, because that's projection is working.
So one thing I wondered about, can you do tasks like sources in remote galaxies, do parallax on those with, like if you had a big enough baseline, like for example putting a radio telescope into space?
That's a very good question. If I go backwards to the almost beginning. Yeah. I forgot to mention about this opportunity to increase the baseline. And also things like New Horizons, which is huge distance from Earth. And also there is this way of doing parallax. We move around the center of the galaxy with a speed of 200 kilometers per second. So in 1 year, we cover tens of astronomical units, or even hundreds of astronomical units. I need to calculate this. So that's another opportunity to look from different positions to very remote objects. So yes, it is possible.
Could you just set up a radio telescope on like Mars or something, and then when they separate, you can do a bit of parallax? For like if you put a telescope on Mars?
On Mars, parallax of Mars.
Like from Mars.
Radio telescope on Mars.
Oh, right.
Oh, yeah.
No, I think initially it will be radio telescope on the moon. It will be the first step. In terms of Mars, well, maybe some robotic radio telescopes, and maybe something orbiting Mars with a nice radio telescope, if we are so keen to measure parallaxes with this high accuracy. But thank you, that's a good question. Do we have any questions from the web? Not yet.
No. Okay, well, there's no further questions. I would like to thank Sergey for a really informative and interesting talk. Really appreciate it. Thanks very much.